Yes, sir.
Okay, thank you. So today we'll discuss about the multi-node network. Okay, so let's see the how many 116. Let's take the attendance first. Okay, so we'll discuss about we actually means discussed about MPI program. So MPI program run over multiple network, multiple nodes or multiple computers, and till now I've not discussed the means MPI works on actually what I can say just like virtual processes. Okay, so processes can be created in any node, and they will communicate among the processes. Okay, and what underlying network? So MPI program it don't assume. So we can write program without assuming the underlying networks. So similar to so writing C program without knowing underlying hardware. So kind of thing. So it is high level, and we are doing uh, multi-process programming, high performance computing programming using that. But we need to know means how internally means people connect the network. Okay, and how we can write good program for that. That also we can see. So multi-node architecture we'll see, and how particularly multi-node architecture means we looked at the network point of view. Okay, and which network is good, how it is good, that in that aspect we'll look at. Okay, so this thing already we have discussed in the last classes, bus network. So it is scalable up to 8. So it is not scalable beyond that. So if it number of nodes or number of nodes are more than bus interconnection network is not good, or shared memory is not good. So in general, if you look at bus is actually shared media and is low cost, lower throughput. But if you consider the switch network, so as compared to the bus, in general, switch network is a switched path and higher cost and higher throughput. But it is we need to go for proper switching network. And most important thing is scalability is better. So switch network is scalability. Switch network means our a general network, what interconnection network we use. Okay, that is a switch network. And this thing already we have discussed. This thing interconnection network. What is topology? So who is connected to whom? Then direct or indirect. Where the switching is done, static or dynamic. Which when the switching is done, and then circuit switching or packet switching, how connection are established. And another thing is store forward or wormhole routing, how the path is determined. Then how switching is controlled, and then whether the mode is synchronous or asynchronous. So among this, we'll discuss first 3 points. So particularly topology uh, and static and dynamic network in this lectures. Okay, and rest of the things we don't require maybe for this course. So detail. People read about this network in network courses, but here we'll discuss about the topology, property of the topology, and static and dynamic network. Okay, so what is a direct network and indirect network? So direct network means this is a computer. So let me change to ledger pointer. So this is a computer. So PMS, okay, processor, memory, and what I can say switch, PMS or storage, you can say, or particularly we can say it is switch. Okay, processor, memory, and switch, processor, memory, and switch, and each computer. This is one machine. This is one machine. It is interconnected with a dedicated link. Yeah, this is also interconnected with a dedicated link. So this is one machine. This is another machine, and in this case, indirect interconnections. So machines are connected to a switch. Okay, and all the machines are connected to a switch, and they will communicate through switch. That is indirect connections. Okay, so in general, direct connections is what we say maybe mostly for static network it is applicable. So we'll discuss about the static and dynamic. And whenever it connects through switches, okay, so dynamic network we can design. Okay, so that dynamic network, one or two example also we'll see. So static and dynamic networks, so fixed point-to-point network connections, usually direct, and each node pair may not have direct connections, routing through nodes. Suppose in this case, so this node, and this node, suppose they want to communicate. So we don't have direct connections. So it need to go through some node. Okay, so this is one node and this is one node. If they want to communicate, then there is no direct connections. But this node and this node, they can communicate directly. This node, they can communicate directly. So what it means, in static network, each node pair may not have direct connections, routing through nodes. That means it need to go through node. Dynamic networks, connection established as per need, usually indirect. Okay. And path can be established between any pair of nodes. So that also we have examples. So towards end we have examples of dynamic network. And this thing already we have discussed, but again was static network topology. So this is very linear topology. There are 4 computer or 4 nodes connected in a linear fashions. This is 2D mesh. Okay, and this is star. This is tree. So we looked at the we'll analyze the property of different topology. Okay, topology means interconnections topology from different point of view. So which one is good, which one is bad, that we'll see. And this is another set of network. So this is ring network. So this is fully connected network. So there are 5 nodes and everyone is connected to everyone. Okay, so this is 5. So whenever you're saying 5, this number of link will be less. So whenever n nodes will be there, how many link need to be there? Can you say how many link need to be there?
NC2.
Clearly NC2. So fully connected means NC2. And this is torus. Torus is actually, if you go back, this is 2D mesh, and for every connection, this is wraparound. So if you do a wraparound connections for every corner node to then that is will be torus. Okay. So this one is these 3 things, and this is a wraparound. That means this is a, if you look at this is a ring, this is also another ring, this is another ring, and this is also vertical rings. Okay. So this is ring connections. So clearly, so for this is 4 node ring. So this is, if you make, in this case, 3 node ring, 3 node ring. There are 3 rings, and vertically 3 rings and horizontally 3 rings. So in this way, it is torus network. Okay. So this is very high level, but we need to analyze which one is good and which one is not good. Okay. So in that way, let's see. So what are the property? There is another network. This is called fat tree network. So this tree network, but whenever you go up, the number of links are higher. We'll see more examples and more clear-cut diagrams of fat tree network. Okay, so whenever we looked at any switch network or topology, so to establish which network is good or which network is bad, so we have some parameters to look at. So quality of topology based on, first thing is degree. So number of link from a node. So this is one parameter. Then diameter, maximum number of link crossed between 2 nodes. Maximum number of links crossed between 2 nodes. This is a diameter. So maximum number of links crossed between 2 nodes. Then average distance. The number of links to a random destination. So average distance between any 2 parent nodes. Okay. So these are the 3 common parameters to decide which network is good. Okay. This is degree, diameter, and average distance. The higher, if you look at diameter is lower, whenever diameter is lower is better. So degree, higher is better. Average, lower is better. Okay. Another thing is bisection bandwidth. So another parameter is bisection bandwidth. Minimum number of links that separate the network into 2 halves. Okay. So with example, I'll show what is bisection bandwidth. Minimum number of links that separate the network between 2 halves. And then is bisection bandwidth. So this is bisections, number of links. Okay, into bisections is a number of links and link bandwidth. If you multiply the link bandwidth, that is bisection bandwidth. So let's look at examples. Okay, so this is a mesh network. This one is mesh network. So bisections across smallest cut that divide the network into two halves. So in this case, so suppose this is a network, okay, and this line divides. So this is bisection cut. So this is a suppose this is a array, okay, and this is your cutting in the middle point. This is for one line. So this is per mesh. So how many places we need to cut? So 1, 2, 3, 4, 5, 6. Because it is 6 plus 6, we need to cut at 6 places. Okay. So how many nodes are there? 36 node in this mesh network. So square root of n. So square root of n is 6. So 6 link we need to cut and link bandwidth. This is bisection bandwidth. And whenever it's a bisections, number will be 6 link we need to cut. 6. So bandwidth across smallest cut that divide the network into two halves. And this bisection bandwidth is important for algorithms or applications in which all processors need to communicate with all others. So bisection bandwidth is important in which all processors need to communicate with all other processors. So do you remember which MPI communications, collective communications use that thing? All processors need to communicate with all others.
Broadcast.
All gather and all scatter.
Yes, all gather and all scatter.
All gather and all scatters. Okay. Broadcast use all processor, but from one processor it goes. Okay. So in this case, what I'm saying is all processor need to communicate with all other processor. So all gather and all scatter they use. Okay. So this is a simplistic example is linear array. So in linear array, what will be number of links? Suppose this is how many nodes? 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes. How many links we require? So clearly n minus 1. So, and what is the diameter? So diameter means what is diameter?
N minus 1.
Longest number of links. So need to cover from one point to another point. So diameter, total diameter is n minus 1. Okay. So maximum distance in the, so what I can say, network, that is diameter. So average distance, it will be n by 3. Okay. So it will be n by 3. Average distance. Okay. And then what is the bisection bisection first? Bisection number. Bisection bandwidth is 1, and if link bandwidth is if you say then 1 bandwidth. So if you cut, suppose bisection is cut into half, equal half. Suppose you put cut here. Okay, then one link, if you cut one link, then it will be divided into 2 parts. Okay, and bisection bandwidth is 1 into link bandwidth. So this is a linear array have this characteristic: diameter, average distance, and bisection bandwidth. So similarly, suppose you look at okay, so ring and torus. Okay, ring. So in ring, so what will be the diameter? Because array is actually, if you look at array is not wraparound. So wraparound is not there. Because of that things, diameter is n minus 1. Okay, but whenever you go for ring, so wraparound, at the corner node will be connected, rightmost node will be connected to the leftmost node. There is one more link is there. So in that case, diameter get divided into 2, means diameter will be n by 2. Average distance, earlier it was n by 4, now it is n by 3. Now it is n by 4. What is the average bisection bandwidth or bisections number? Bisection bandwidth. So it will be 2 link we need to cut. Then only we can separate into 2 equal half. Okay.
Sir.
Yeah.
Sir, how average distance is being calculated?
So take distance between all pair of node and divide by NC2.
Okay, sir. Thank you.
You'll get this average distance. Okay. And this is mesh network. So mesh network, what is the diameter? So in this case, how many node? This example have 36 node. What is the diameter? So clearly you can see
from the top corner to bottom corner.
Yeah, leftmost top corner to bottommost right corner, or other way around. So any this corner to this corner or this corner to this corner. Okay. this corner to this corner, or this corner to this corner. Okay, so this is the diameter, and this can be zigzag path also. Okay, so what I can say, not only this path but other path also. So you can say not only this path but this is one path. This one is one path. Okay, but other path may be this. The distance will be same. Okay, distance will be same. So exactly same. Square root n minus 1 into 2. That will be the diameter. And what will be the bisection bandwidth? Bisection bandwidth is how many? In this case, 6 node need to be cut to divide into equal half. So that is square root of n. Okay. So here 36 node, we need to cut 6 link. Okay, this is diameter and bisection bandwidth is the one parameter. You see. And how many links we require? So in this case, how many link total to create a mesh network? How many link? So if you look at for every node, so internal node, so how many what I can say connections you require? So it have 4 neighbor. So take any node in the internal node. So not the boundary node, but take internal node. So take any internal node. So how many? Take any internal node. How many connections is there? 4 connections. Every internal node have 4 connections, and it is shared by 2 nodes. Okay, so how many link you require? So suppose n node are there. So and assume all are internal node. So you can say n into 2. For every node we have actually 2 link we require. So 2n link we require. Up to 2n link. Okay. It is clear?
Excuse me.
Yeah.
Sir, how do we calculate the average distance between nodes in this case?
So in this case also average distance. So I'm not sure I've calculated or here, but we can calculate. So in this case also average I have not calculated here. How to calculate also we need to look at the formula and do the calculate. So all pair distance, sum of all pair distance by number of nodes.
Okay, sir.
Okay, and it can generate to higher dimensions for mesh. Okay, natural algorithm for 2D and 3D arrays. So mesh network is mostly used. So I am showing one examples of mesh network. So let me go to my system. So if you look at Intel GNP, so there is a. Have you heard about one processor, Intel GNP processor? Intel GNP processor, KNL, night learning architecture. So they have actually 2D mesh network. So this is actually. Are you able to see my screen? Yeah, right side you have one picture. So this is actually 36 tile connected in 2D mesh. So this architecture means even Intel processor, inside the processor also they use this kind of tile architectures, okay, or mesh architectures. Okay, so each node you can say is tile, and they are connected in a 2D mesh. Okay, this is the natural means mostly mesh connections are natural connections. Okay, and the previous version of Intel GNP, they used to have actually ring network. Okay, so recent version are they're coming with actually what I am showing is this one. Are you able to see the screen? So this one actually number of core are less, but they used to get with the ring network. So this mesh network, ring network. So people have already implemented in architecture, and at higher level anyhow we can connect in any mode. Okay, so based on our switch and interconnections. Even in architecture also this got considered. So ring network and mesh network. So these are two popular network. Okay. Okay, so let's move forward. So this is 2D torus. What is the difference between mesh and torus? So Are you able to see? So diameter is here 2 square root n minus 1. Okay. And in torus, whenever it says, because we need to take this path, longer path. So full longer path. So we need to take full longer path. This is the diameter. But in case of torus, so the diameter is square root of n. So square root of n means the here 36 node. So 6. So n to n will be 6. Okay. So maximum distance from, suppose you take distance from this node to this node. So how much you require? Suppose this left corner to right corner. How you can go?
So we can have two links.
Yeah, means this node, then from here you can go to this node. Suppose from here to we want to go to this place. So this place, here to this place. Here to, suppose not this place, maybe up to this place.
Middle.
Yeah, middle. So then it require 6 link. So we need to come to this place, then come to this place. Square root, diameter will be square root of n. And bisection bandwidth, in this case, 2 into 1 square root of n. So earlier case it is square root of n, but now every place has not one link, but two link. In this case, one link is there. Are you able to see this thing? One link, but in this case, clearly you can see if you want to cut, then you require 2 link. So let me cut. So if you want to cut the things, whether I can draw a line or not. So this one. Oh. So if you cut this, then how many link is getting cut? So earlier it was 6, now it is 12 link is got. So bisection bandwidth is 2 into square root of n. Okay, so this is also naturally many algorithms we write in actually 2D and 3D arrays. And this is mesh and torus, more generalized one. So in terms of order, if you look at, then diameter is order of square root of n, and bisection bandwidth is order of square root of n. So if you look at in terms of order, whenever you looked at order, then in general constant thing we 2, and this in this case another 2, that we ignore. Okay, so by default, whenever mesh and torus in terms of order we say, then order of square root of n, square root of n will. Is this clear?
Yes, sir. And sir, torus is much better than mesh because it has lower diameter and higher bisection width.
Yeah, but whenever you say means n is very large, and we looked at in terms of order, then for both the cases it is similar, only 2 times. Okay.
Yes, sir.
Here mesh is 2 into square root n minus 1, and bisection is square root n, and in this case square root n and 2 into square root n. So if you look at in terms of order, then both are similar. Okay. So if you look at exact number, then torus is better off. Okay. But torus will be costly because you require more number of connections. Okay. And now let's come to another thing is that is called Hypercube. So all the things previously whatever we see, so linear network, then ring, then mesh, torus, it's looks very what I can say trivial kind of thing. But whenever you go to means let's look at Hypercube, how Hypercube get built, and what is the benefit of Hypercube. So this is the this one is let me change to this one. So this one is 0-dimensional Hypercube, and this is 1-dimensional Hypercube. Okay, so 1-dimensional Hypercube we have 2 node. Okay, and 2 node connected by how many link? 1 link. And this is actually 2-dimensional Hypercube. So in this 2-dimensional Hypercube, so what do we do? There are 2 1-dimensional Hypercube, they are interconnected. Okay, so 1-dimensional Hypercube, who have 2 0-dimensional Hypercube, and they are connected with one single link because they have 2 nodes. So in this case, we are taking 2 1-dimensional Hypercube and we are interconnecting all of them. Okay, all of them means corresponding one. Okay, so in this case, what we are taking? We are taking 2 2-dimensional thing. Okay, and we are trying to interconnect between corresponding one. Are you able to understand this thing? Okay, then we are moving towards 4D. So we are taking two. So if you look at, in this case, we are taking two 3D, two 3Ds, and we are trying to interconnect them. So corresponding one. So in this case, so diameter will be log n and bisection bandwidth with n by 2. So if you look at this 3D case, 3-dimensional hypercube. So how many link you need to cut? So total how many nodes? 8 nodes. So 8 nodes, and if you want to cut into 2 half, then how many link you need to cut? So 4 link. Bisection bandwidth is 4 link you need to cut. And suppose from this node, so you want to go to this node. So how many link you need to go? So clearly x directions, y directions, and z directions. So how many dimensions? One is more than enough. Okay, so in this case, go to this node, then this node, and this node. So clearly, so based on number of dimensions, so diameter will be this dimensions. Diameter will be dimension, and dimensions will be log n. Okay, so diameter will be d will be log n, and bisection bandwidth will be n by 2. So this network is somehow better network. So better network. So our diameter got changed to log n. What is the torus network, mesh and torus? What is the diameter? Mesh and
Over
torus.
root n.
Theta of root n.
Root n.
Yeah, root n, square root n. So and here is log n. Okay, suppose you want to connect into 1024 node. Then what will be the diameter? So 1024 node means log n, so it's 10. Okay, so you'll get into means diameter will be only 10. So diameter means it says that what is the means longest path we can see. Okay, so diameter is longest path we can see, and in Hypercube longest path will be only log n. And bisection bandwidth. So if you want to cut into equal half, then you require to cut n by 2 link. Okay, so n by 2 link. That means it is more robust. Diameter is very small and is more robust. Okay, so in that way, Hypercube is the one of the best interconnection network we can see. But only thing is number of links. How many links we require? Okay, so it is popularly early messages. Many actually supercomputer. So earlier days supercomputers, so they used to use this link. Okay, and for every suppose you want to go from one node to another node. Okay, so then you can do a gray code addressing. Each node connected to other node by 1 bit different. So because binary coding you can do. We can do binary coding. So this is gray coding you can use for each coding of each node. Suppose this one. So this bottom one. Are you able to see this bottom one? So this is 000. This one is 000, and this one is 001. Okay, so this is only last bit changing. Last bit changing. So in this case also, if you look at 010 and 101, this is only 1 bit changing. For every neighbors, okay, every neighbors will have only 1 bit change. Every neighbor will have 1 bit change. And suppose you want to go from one node to another node. So how many maximum bit change can happen? Suppose in this case it is 3 bit.
So maximum 3 changes can happen log base to n.
Yeah. Suppose instead of 3, in this case 3 bit are there. Okay, 8 node. So suppose n nodes are there. So maximum log n bit changes can happen because each node can be coded into binary with means this gray code. All numbers can be done in gray code. So here communication will be much easier also. Coding also much easier. Okay, so Hypercube, same thing I am showing graphically. Yeah.
Sir, but will there not be one problem of there that the links are too many? I mean, links
Yeah.
will keep on growing exponentially, right?
Links will be too many. So links, what will be the number of links? So
Exponential?
every node have how many links?
For each
Diameter.
node, there are log n links.
Yeah. So number of links will be n
N log
into
n.
log n. N log n links you require.
Okay, okay.
So it will be costly, but what you get is actually a very nice thing.
Yes,
Okay.
yes.
So we'll have a comparison sheet. Okay. So let's say Hypercube. So how you build up. So whether you are able to see the my animation or not. So 0D, 1D. Then this is actually 2D how we are making. So we are taking two 1D and we are trying to interconnect. Are you able to see? Okay, so two 1D and we are interconnecting and making 2D. So this is two 2D and we are trying to interconnect. Are you able to see this thing? How we get 3D? All corresponding will be interconnected and can be done very nice binary coding. And how we can go for 4D? So 0, 1, then connect all of them. So in actual animation, it looks very nice. Okay, so in this way, we can build up the Hypercube network. So we'll do a comparison. Okay, definitely we'll go for a comparisons. And the most important thing is diameter is log n, bisection bandwidth is order of n. So n by 2. Okay, so it is, if you look at in terms of order, then it will be n by 2. The exact number is n by 2, but it is order of n. And this is tree network. So this is another very simple thing, tree network. So in tree network, how many link you require? Suppose n nodes tree, how many link you require?
N minus 1.
N minus 1. So number of link will be much lesser. What is the diameter? Going from any node to any node.
Order of log n. If
Order of log n. So what you are losing here? You are losing the bisection bandwidth. So in bisectional bandwidth, it will be only one. So cut any this guy. So cut in this guy, then it will be done. So it will be separated. So it is not robust network. It is a good network, but it's not robust network. Okay. But many algorithms use actually means tree fashions. Okay, so tree fashions are what I can say in our algorithm codes also. So we generally try to formulate the problem in tree format or hypercube format so that we can get actually means very good better complexity, log n complexity or means log n complexity. So actually means tree networks are very good in algorithm design. There are many tree algorithms are there. Algorithms are there means many applications was written assuming the tree kind of interconnections. Okay, then it is easy layout, planar graph, because tree will be always planar graph. Okay,
Excuse
because
me,
number
sir.
of nodes. Yeah.
Sir, if my bisection bandwidth is low, what exactly is the problem? Like concretely, what is the problem?
So this bisection bandwidth one means this will be actually bottleneck. Suppose you do a means all to all communications, all gather and all scatter. Then this link will
Okay.
be very heavily
Yes.
loaded. And another
Yes,
thing
yes.
is this is not robust. Suppose this network get cut. Then what will happen? Your whole system got cut. Your bottleneck is gone.
Yes, sir. Thank you.
Okay, so our India, there's a Siliguri corridor is chicken neck corridor, people says. Okay, so that is the major to come from mainland India to northeast. So the Siliguri corridor is the chicken neck kind of thing. So in this case, tree, this one will be the chicken neck. If someone cut this node, then done.
Okay, sir.
Okay, got. So this is tree network, and then to solve this problem, what we do? Suppose if you are going towards a higher level, not the bottom level of tree, so increase the, what I can say, number of links. So fat tree avoid the bisection bandwidth problem at tree, more wider link near the top. Okay, so how you can do? So kind of like this. So whenever you go up, put more networks, more links. Then it will solve the problem of your bisection bandwidth. We have more bandwidth, and in this many places people use this thing, bisection bandwidth, means what you can say fat tree network. So so whenever you try to connect to server, so we generally connect with high speed link, and whenever you connect with very low level machines, we connect with very any link, smaller link. So this is natural also. And in this case, what we are getting? Diameter is also log n. Diameter is log n. Suppose you want to send data from this node to this node, this node to this node. So what is the path? So you need to go to this path and then come back this path. So 2 plus 2 log n. Because if you arrange in a tree pattern, then how much? So maximum path will be 2 log n. Okay. And this is if you look at other way around. So this right side diagram is what we are trying to say is actually this left side is a thick line, and here we are saying 4 links, 4 or 5 links we are putting.
Uh, sir, sir, at the places where two links cross each other, like in a T joint, so should
Yeah.
that not be considered as another node?
Yeah, this will not be considered another. Nodes are actually on the bottom. So these are the nodes. These are the nodes, and these are actually links. These
Sir,
are the
but
links.
at least there should be some kind of switches at the junctions.
Some switches. Some switches will be there. Some switches will be there. Okay, all means nodes will be in the bottom layer. And let's compare. So this is the comparison chart. So n is number of node and small n is dimensions. So what do you see? So one dimensional mesh. So degree is 2. Okay, one dimensional mesh, 2 dimensional mesh. So diameter is n minus 1. So is not one dimensional mesh means what is? This is an array. Okay, so one dimensional mesh is array. Okay, 2 dimensional mesh is actually proper mesh. Okay, this is 3D mesh and this one, and this one is ring. This is 2D torus. 2D torus is also same as mesh. Okay, this is hypercube. Hypercube diameter and degree. So per node, okay, so log n link required. So in this case, per node, only 2 link, left, right. In this case, north, south, east, west required. Okay. And here diameter is n minus 1. So here square root of 2 into square root of n, that is this is square root of n. And then in this case it is log n. So hypercube degree is log n. That means you require more number of link, but diameter is in log term. Average distance is n by 2. Okay. So and bisection bandwidth is n by 2. So here n and this small n is dimensions. So what I'm saying is dimensions. Okay. Okay. If you look at n, then it will be log n by 2. So average distance will be log n. Okay. So in this way you can compare. So crossbar we have not studied till now. So crossbar we'll see. Okay. This comparison chart is fine. Hello. So main highlight is actually this one. So hypercube, then ring torus or whatever you say, 2D mesh, or this is array, array ring, mesh torus and hypercube and tree. So if you look at tree, so tree, what is the link? So if you look at means all the places of nodes or intermediate nodes are there, then means two, what you can say, parent, one parent and 2 children. And bisection bandwidth will be this one, 1. But distance will be average distance and diameter will be 2 log 10. So in this way, degree defines how many, what will be the cost. Degree defines what will be the cost. Diameter defines what is the means of worst case distance. Average distance will overall means all pair of node by all pair of means what you can say by divide by total combinations. Okay, all pair combinations. And then bisection bandwidth is actually how robust it is. Okay, so if you look at which one is robust, so if you look at this one, will be more robust, n by 2. So n by 2 is robust. So this is diameter is less, but link is higher. Okay. And if you look at all pair network, suppose all to all connections, what will be the diameter? All to all connections. Suppose you take all to all connections, all pair connections. So you connect all node to all node. So what will be the diameter?
1 will be the diameter.
1.
Average distance will be 1. What will be the bisection bandwidth?
Sir, we'll have to
Bisection
break the
bandwidth.
entire.
All pair. So how many link?
NC2 links we'll have to break.
Order of NC2 link we're going to break.
Yes.
And what will be degree? The degree is n minus 1. And total number of link will be n square.
Right.
Okay, so total number of link will be n square. So in that way we can go which one is costly, which one is robust. So in that way, if you compare all the things, then Hypercube will be the winner. Okay, so Hypercube is actually means one kind of winner.
Excuse me, sir. Sir, this ND mesh and Hypercube, which one is better? I mean, ND mesh also has very nice complexities, right? N raised to the power 1 by n and all those.
So n-dimensional mesh.
Yes.
ND mesh is also comparable, but it's actually in this case diameter. So n to the power n minus 1 minus 1. So in that way, it may n-dimensional mesh will be also it will be costly. In terms of cost, it will be very high. If you look at n-dimensional mesh, this one is very dangerous. Degree is 2n. And how many link you require? Total link 2n into n. Oh, not 2n. So this is no. This is it will come down to log n only. That is 2 log n. It will be 2 log n. So 2 log n will be again. If you compare Hypercube and this thing, then this is 2 log n and this is log n. So Hypercube will be a little bit less costly as compared to n-dimensional mesh.
Sir, I think here it would be 2 times capital N to the power 1 upon the degree.
So which place?
Sir, where you wrote 2 log n, it's not log n, it's capital M to the power 1 upon degree. Because when you multiply with d, then you will get the expression.
But still, it will be costly, I think so.
Yes, sir. The login is asymptotically better.
So this is the comparison chart. Okay. So and let's move towards only funny things. So people go for multi-level network also. So we have seen many hierarchical network. Okay, then let's see multi-level bus also. So people can think of this kind of things, multi-level bus. Okay, hierarchical or multi-level bus network. So if you look at your PC, so PC have this kind of architecture. So they have multi-level bus. So they have actually high-speed bus and low-speed bus. This is actually core bus and non-core bus. So between processor, they connect with different bus, and whenever they connect to the other peripherals, they have different kind of bus. Okay. So South bridge and North bridge. So Intel have actually any means motherboard. They have South bridge and North bridge. So North bridge is faster bridge. They connect processor and memory, and South bridge is actually they connect all peripheral and all things. Okay, so this is also one kind of, and in PC or domain, or if you want to connect many nodes or computer also, we can go for hierarchical bus. It will be save time also. Okay. So this upper level bus, you can go for high speed one. Lower level, you can reduce the speed, just like factory kind of thing. Okay. So this is another funny guy, but we don't see what you can say in comparison table. And this is ring of ring. So what you thought of ring? Okay, so now it is ring of ring. Okay, ring are simple but have low performance and lack of robustness. But these are ring of ring. So this is bigger ring. Okay, this one is bigger ring, and every node is a part of another ring. This is local ring, and this is part of global ring. Okay, so one node of each local ring is connected to a global ring. This is the local ring, and this one is global ring. So ring of ring, second level ring. Okay, so 64 node ring of ring architecture composed of 8 node local rings and 1 second level of ring. So this is another kind of network. So can you think of 2.5D mesh? Okay, so 3D mesh is this one. Okay, so let's look at 2.5D. 2.5D means, so you have 2D mesh and you connect the 2D mesh on a backplane. Then it will can visualize as 2.5D. So these are for showing purpose I am showing. It is interesting things to know. And stronger and weaker connectivity in mesh. So have you heard about this kind of interconnections? So in this case, in regular mesh, in take any internal node, how many interconnection was there? Regular mesh. There used to be only 4.
The dimension. Yeah, the 4. So
here, internal node are connected. They have actually 8 neighbors. So take any of this internal network. So this guy have how many neighbors? So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 neighbors. That means mesh have 4 neighbors, north, south, east, west. But this guy have actually 8 neighbors. So definitely every node have actually 8 neighbors. That means whenever you have more neighbors, then what do you get? Actually, bisection bandwidth will increase. Okay. Diameter may not change. Okay. But still it may change because earlier we need to go to this path, but now we can go directly. So diameter may reduce, but not drastically in terms of order it may not reduce, but in terms of number you can reduce. Okay. This is 8 link per node. So write one. How many link per node? So take this guy. So take 0. 6. So in this case 6. This guy. These are the 1. So what I'm saying for 0th node, this guy, 6 link. So every node of 6 link. So this is actually little bit not stronger as compared to the earlier one, but still it is stronger as compared to mesh. This is called fortified mesh. Okay, so fortified mesh means extra mesh with extra connections. Okay, or other model with stronger connectivity, 8 neighbor or 6 neighbor in terms of triangular or hexagonal node. Okay, so as higher dimensional meshes, greater connectivity, but does not automatically translate to greater performance, but it reduces the congestions and increase the bisection bandwidth. Okay, so this is if you want to reduce the what I can say cost of mesh network. Suppose you want earlier case we want to increase the mesh of we want to add some fortified mesh. We want to add something, but suppose you want to remove something. Suppose simplify thing. Then what we are trying to do? So instead of 2-dimensional link, okay, mesh in general it is 2-dimensional link. We go for 1-dimensional link. So this is kind of ring, 1-dimensional. This is not 2-dimensional, 1-dimensional one. Okay, so this is simplifications. So have you heard about this 4x4 Manhattan Street Network? So one-way traffic. Have you heard about this one-way traffic? Many places, those who have actually this kind of road network, so they use Manhattan Street traffic control to do street control, traffic street control. They use similar kind of thing. Okay, so 2 in and 2 out channel per node. So earlier for mesh, every node have 4 channels, in-out channel, but here 2 in and 2 out channels. So half the net length. And with even side length, the diameter does not change. Okay, some shortest paths become longer. And sometimes it is cost effective. Why you are saying cost effective? Because you are removing some link. And this is another thing. So 2D mesh is there, and on top of that, we are equipping a global bus. Okay, so this one is global bus. So this link is internal link. These links are actually mesh links, and whatever the one coming out. Okay, so these links, particularly these links, this is actually connected to a bus. This is bus. Every node is connected to this bus. That means how it will be. So what purpose it will be useful? Suppose if you take a hypercube, okay, so if bisection bandwidth is good, then all-to-all communications will be better way. Okay, so in this case, suppose broadcast, you want in your applications, you require a lot of broadcasts among the process. Okay, so only broadcast, not all-to-all communication. Suppose you require only broadcast. Broadcast need to be done very efficiently, and rest of the things can be done means local communication. Then this kind of network will give you better benefit. So if application demand lot of broadcast, okay, demand lot of broadcast, then this kind of network give you. So you create a separate, augment the mesh or augment a tree with bus. And that is specialized channel for broadcast you are doing. So the single bus increase the bisection bandwidth by 1, but broadcast the result to all node in one step. So this will improve the performance. So suppose you, based on your applications, how you write the applications, and based on that you design the network, then it will performance will be much better. But whenever you write MPI program, so MPI program, so in generally programmer don't need to worry about this, because suppose you are an engineer, when you want to improve the performance of the system, write a good quality program for a specific network, then you can transform the program or rewrite the program, or you try to re-engineer the network so that your program will work better. Is this clear? Hello?
Yes, sir.
I'm trying to see the time. So 3:53. So let's go to another 7 minutes there. So one more things will be clear. So some people ask, what is dynamic network? So what is dynamic network? So dynamic network is actually switch. Okay, so it is a switch, and nodes will be connected to the end. Okay, so towards end it will be connected, and this is the simplest 2x2 switch, and this one is left one is a state connection. What is communications? So top one is communicated to top one. This is bottom one is communicated to the bottom one. This one is exchange. Top is communicated to bottom, and bottom is communicated to top. And this one is upper broadcast, and this one is lower broadcast. So with simple 2x2 crossbar switch, we can do 4 kind of communications. Okay, 4 kind of arrangement, we can say configurations. That is better word. 4 kind of configurations: state configurations, exchange, upper broadcast, and lower broadcast. This is K crossbar can have differently, but using the simplest 2x2, we can make K crossbar. But let's look at using 2x2, how can design the bigger one. Suppose you want to design a 8 node. Okay, so suppose you want a 8 node connections. Okay, so here one computer is there, here one computer is there. So there are 8 computers connected to 8 computers. This is not 16 computer. Okay, this 0 and this 0 are same. Okay, this 0 and this 0, they connected to same computer. Okay, so left side, this one is C0, and the same C0 is connected here also. Okay, and this is C7. This is also C7, same C7, and they are connected using a baseline network. Suppose baseline network means internally you have 2x2 network, and this is a dynamic network. Whenever you require, create the network and communicate. And in this case, blocking may occurs, because in this is blocking examples. So suppose 105 and 6 they want to communicate to 6 and 7. Okay, 5 want to communicate to 6 and 6 want to communicate to 7. Then this node, this particular link, okay, this link, because here there will be a, so if you look at this thing, so if you go up, so these things 2 cross 2 have this thing, so this requirement. So from the top also it need to come to bottom, okay, and from the bottom also it need to come to bottom, okay. So because of that reason, there will be a conflict, and that will be a blocking, because same link in this case need to be used, because here supposed to have one link like this, and it will be used by two communications. It will be used by two communications. So that's why blocking may occur. One need to wait for others. But if you go for, suppose this is how many internal stage? So if you look at this stage 1, stage 2, and stage 3. So this is baseline network, and it has only 8 nodes we want to connect with 3 stage, 2 cross 2 switches. Then blocking may occur. But if you go for 5 stage, so 2 log n minus 1. So earlier it was only 3, and now I've increased to 5 stage. Then blocking will not occur. So everyone will can connected to other guys simultaneously. That means NC2 connections, 8 C2 connections can be established very nicely. But can someone compare with the all-to-all network? So all-to-all, how many? Suppose 8 node, we want to connect to all 8. So how many link you require? 8C2. 8C2, what will be value? Hello, 8C2, what will be value? Maybe 28?
28, yeah.
28.
28. But here, we may require more than 28 link. For 8 case, we may require more, but it is a stage-wise one. It is easy to design. So only thing it is easy to design, and it is hierarchically you can design. Hierarchically you can design. So this is a dynamic network, and connection get established during the communications. Okay, that's why it is dynamic network. Baseline and bench network. So these are the two things we covered, and next is whether we have time or not. Let's see. It's already 3:58, so we don't have time. So, but still 1 minute I can say. Suppose this kind of thing. Suppose you have a tree algorithm. Okay, so you have written your program assuming a tree. Your network is tree, and whenever you run your code, then internal the what I can say, interconnection is not tree, it is mesh. Then how to do? Okay, suppose you have written a just like virtualizer kind of thing. So you need to do some virtualizing. Suppose you have written a code for tree and you want to run in mesh. How to do? Or you suppose you have written a code for mesh and you want to run in tree kind of network. Suppose you have written an MPA program, assuming that your HPC system have tree network, and suppose you want to run that code on another HPC system where the underlying architecture is mesh network. So how to map them, or should you simply go and run that code? So can you say any how we can do? So this concept is called embedding. So we'll discuss in the next class tree embedding or network embedding. So one network you try to embed to another network. A kind of virtualizing, kind of do a virtualizations, run window machines on top of Linux or Linux on top of Windows. So how efficiently we can do? So written program for mesh, but your underlying architecture is something else. We want to run efficiently. How to do? How to just configure? Is this clear? So next class, tomorrow we'll discuss about the network embedding. Okay. And then we'll move towards the scheduling.
Yes, sir.
Okay. So you have
sir,
any doubt you can ask? Yeah.
Yes, sir. So, sir, in the dynamic network, we are using switches.
Yeah.
But like even in the tree network as well, we use switches to establish connections.
But that is static at the time of communications. Okay. So this is, it need to go through node. Here it need to go through switches.
Okay.
So nodes are outside. Static networks, so nodes are goes through, link goes through nodes. Static network. And dynamic networks, so inside the network only switches are there. Okay. So nodes are separated. So in that way you can think.
Okay.
So any other questions? Then you can stop the class. Let me stop the recording.